Okay, the next speakers are going to be Daniel Milroy, computer scientist at Lawrence Livermore National Lab, and also Vanessa Sochat, computer scientist at Lawrence Livermore National Lab. So the topic is going to be orchestrating the future ensemble workloads in an age of converged computing.
So we're going to start out with the video, and I will talk interspersed with Vanessa.
Ensemble workloads in the age of converged computing. Let's get started. So if you've looked around recently, you've probably noticed. Hi folks, I'm Vanessa Sochat, joined by Daniel Milroy. We are from Lawrence Livermore National Laboratory, and we are very excited to be here today to talk to you about orchestrating the future, ensemble workloads in the age of converged computing. Let's get started. So if you've looked around recently, you've probably noticed that workflows are becoming increasingly complex. And in fact, this reflects the sophistication of the science that are behind them. And so what you're looking at is an exemplar of one of these workflows called MUMI. MUMI means the multi-scale machine learned modeling infrastructure. The name is a tip of the hat off to the Moomins, which was sort of a book comic series of about 8 or 9 books published between 1945 and 1993 by a Finnish author. The Moomins are so kind of a cute little round white hippopotamus looking creature, but they're not hippopotamus, they're Moomins. Anyway, so MUMI itself is actually modeling cancer causing protein interactions. We use mini MUMI in a lot of our work because it's a proxy application to it. So high level, these emerging workflows have a combination of AI/ML, simulation, orchestration, and then service components. So let's talk about what that means for MUMI. We start out with a machine learning server where we're generating structures. Each of these structures needs to go into a simulation. Now the simulation has 2 steps. The first is create sims, which is the setup, that's in green. When that is successful, that moves into CG analysis in red, which is where the full simulation happens. And actually these 2 steps are very interesting, not just because they're kind of related, but because you can actually run each on CPU or GPU, and that gives you really interesting questions to ask with respect to resource selection and scheduling in the infrastructure that you're running on. Now, all this needs to come together, of course, with a workflow manager. Traditional MUMI used Maestro, which had a job adapter that basically gave the requirements of a job, handed it over to Flux. Flux would then say, these are the resources that I need. Let me look in the graph and figure out what to do. And to have some additional communication between the workflow manager and the machine learning server, we needed to use RabbitMQ for a message queue, like, hey, machine learning server, we need more samples. And then the machine learning server would be like, yes, right away. So what were some of the problems with this approach? Well, production MUMI was run on an HPC cluster. And in order to run it, we needed a DAT. And this DAT needed to request all the possible resources that MUMI could need during its entire life cycle. And so if you look at the plot on the right, what you're looking at is that MUMI has an hour period in the beginning where it needs to ramp up. It actually can't use a significant number of resources until it gets to that. And so what does that mean if you look in the graph on the left? Resource occupancy for CPUs was only at about 50%. And so when we have this all or nothing approach with a DAT, that means that our resource utilization is poor. We think that we can do better. So let's step back and ask, what do we want the future to look like? And let's talk about this in terms of features. The first feature we're interested in is portability. I want to be able to take my workload step that ran in environment A, and I want to seamlessly move it to environment B. I want to run things where they're best suited to run, not just based on resources, but on costs. but maybe also availability. As many in this room may know, it is often very hard to get GPUs. For example, let's say you're running in the cloud and it's like, oh no, I can't get a GPU right now. What do I do? Well, in the future, we can hop in our spaceship and go back to the Batcave. I mean, the on-premises cluster that looks a little bit like a Batcave, doesn't it? So then we kind of pick up work and then we say, oh no, I really needed that nice API, that nice service that the cloud afforded. Let's get back in the spaceship with our sunglasses and go back to the cloud. So the point is that we need to be able to move seamlessly between these spaces. And what we're increasingly starting to see is that portability is a metric of performance. It does not make sense anymore to have your team spend 6 months optimizing an application to run the best that it possibly can in one environment, when maybe you can build it more generally to run across many environments and actually get the work done faster, get the science done faster, and maybe even for a smaller cost. This is the new sort of trade-off, the set of balances that we're considering under these new paradigms. The next thing that we want is elasticity. So going back to this design of something like Mumi, our resource needs change throughout time, and we want to be able to adapt to that, scaling a cluster up and down based on the workload needs, maybe also bringing in different nodes or instance types. Because the way that we run it now on traditional HPC with this all or nothing data approach, there is a huge amount of unused capacity, and we can do better. The third thing we want is dynamism. We want our orchestration tools to respond to state. Traditional DAGs, directed acyclic graphs, cannot account for uncertainty in loops or cycles. And guess what? These new emerging workflows, they have a lot of that. So again, what could we do better? So here's an example. If you're sampling from our machine learning model in Mumi, maybe if you fail, you don't want the entire job to die. You want to adjust the parameters and retry. You want to keep retrying and adjusting in a specific way, particular to that job. And then when you succeed, you want to move on to the simulation. Now, this is why we've been talking a lot about converged computing. And I know I've talked about converged computing at this specific venue before. I'm going to give you a quick reminder. It is the convergence of technologies and cultures between spaces, a best of both worlds approach. And guess what? It is not the technology that is the most challenging of these two things. It is the people. The challenge is people. And so if we go back in time to, say, 2015, and we think about what a conversation between someone in the HPC community and someone in the cloud community might have looked like, it might have looked like this. A battle between fire overlords and worlds. And well, clearly someone here does not skip a leg day. I won't tell you who's who, but the conversation might have gone something like this. You're too expensive. You're dinosaurs. And then it's like, well, yeah, we do have that one cluster with GCC 4.9.3, but like we can't get rid of it because someone needs it. And but yeah, that is a fair point. There's a little bit of dinosauring going on here. Fair point. So maybe we can be friends. Maybe we can work together. This is the good mindset to have. So we're using converged computing. We champion it because we want to ensure that the needs of the scientific community are represented in the broader space. We want to combine the best of both worlds in terms of technology. We want to make applications portable between spaces and get rid of this really, ill-adapted dichotomy of cloud versus HPC. It's adversarial and it serves no benefit. And Flux has been created to address many of these challenges. So portability, elasticity, dynamism, but we also believe, and the reason that we're here today and we're spreading the word of Flux, we also believe that it can address a lot of the cultural challenges too. And so Dan is going to be talking more about Flux later in the talk, both the history and the background. And to be true to what I said, we regularly invite really big, scary fire guy to many of our meetings in this exact room. That's right. Alrighty. So if you take nothing home from this, remember that the success of our science depends on our ability to be collaborative. Keep that mindset in your head. Anytime you think of saying something like, that's too expensive, we need to work together. And so what is the agenda for today? I'm going to hand it off to Dan, who's going to talk more about Flux and different models of convergence that we've worked on and we continue to work on. Dan's going to hand it back to me, and then I'm going to talk about a new model for workflows And then one of the models of convergence, user space Kubernetes. And we're going to be taking questions from all of you. On that note, I'm going to hand it off to Dan. Take it away, Dan.
Wish I'd thought of something to entertain you while we're waiting for the slides to come back up. Thanks for bearing with us. And thanks to the AV folks for facilitating this transition. Yep, looking like progress. Okay, the slides are up. And we fast forward through everything you just saw, hopefully not too far. All right, perfect. Why don't I take it away at this point? So I'm going to give you, for those of you who were here on Tuesday and saw the workshop, I'm going to give you a brief overview of the Flux Framework, and if you might have forgotten when you were here on Tuesday, or if you weren't here on Tuesday, again, just a brief overview, touch on some of the points that we talked on Tuesday, and reinforce some of them in this context of converged computing and models for combining HPC and cloud together. So just to refresh your memories, when you hear someone talk about Flux, at a high level, they're really talking about something like a component that's a workload manager that combines two really important features for complex scientific workflows and for traditional scientific workflows and for cloud native workflows to a degree too. And that is one, hierarchical job management, and two, directed graph-based scheduling. So when I say workload manager, what I really mean is an application or a system that receives units of work. You can think of these as like being components of an MPI-based ensemble of scientific simulations. And then the workload manager ensures that the requests for those resources are mapped to the correct resources. It's planned in time, it's assigned, so process management is performed, and then executed on typically a cluster of computers or a supercomputer. Then that workload is torn down, and it also ensures various other important properties like user fairness and priority. So in the context of Flux, we talk about hierarchical job management, and what do I mean by that? Well, basically it means that Flux can instantiate itself inside of itself or inside of an external resource manager. So your jobs, and Flux can be a job in that sense, can be nested and launch smaller instances inside of each other with kind of a top-level unit of work. And that enables divide and conquer strategies, which can be beneficial in terms of increasing throughput and also customization of that hierarchy of schedulers and resource managers. Now, the second part that's related to this actually is our directed graph-based scheduling framework. So we use a directed graph, a mathematical object or data structure of a directed graph to model the set of resources. And those resources, you can typically think of them as, you've got your nodes, your cores, your GPUs, your memory, et cetera. But we can also model anything that is adaptable or that is translatable into a directed graph. So that can be flow-based resources such as power, networking, storage, et cetera. And having the ability to model and schedule things as a directed graph is extremely beneficial when it comes to any sort of resource dynamism, because when we cast it in the format of a directed graph, then changing those resources in time just becomes straightforward implementations of graph editing algorithms. Also, I should mention that the hierarchical approach and the graph-based scheduling interface really, really well. So to mention something that I talked about very briefly on Tuesday, 2024 was actually a really big and important year for the team. We're managing and scheduling 6 machines on the November Top 500. That's El Capitan at Lawrence Livermore, Tuolumne, which is the smaller sister system that provides unclassified research and access. We're running as a system scheduler on El Dorado at Sandia, which is one of our sister laboratories. And then we have several other systems that are closely related to El Capitan on the Top 500. Now, I should mention that there are numerous existing user mode deployments worldwide. And what I mean by a user mode deployment is basically deployment that sits underneath or is deployed underneath an existing resource manager or scheduler, such as Slurm, LSF, PBS, et cetera. And that's where the predominant deployments are, actually. So let me talk a little bit about the timeline of Flux and where it came from, how it came to be, et cetera. So the project was actually established and staffing was formed and the proposal was funded in 2012. And Flux was actually developed by some of the people who created Slurm to begin with. Now, in 2013, we had a design review, or I should say the Flux team at that time, I wasn't part of the team yet, had the original design review. Then in 2014 was the first instance launch, and this was the user mode instance. So in other words, this is the instance that's actually run underneath external resource managers and schedulers. Then in 2016 was the first public release of Flux Core 0.1.0 on GitHub. In 2018, we had the first public use of Flux for Science in the Pilot 2 Cancer Moonshot Ensemble. In 2019, we had the usage of the multi-scale machine learning modeling infrastructure with Flux. Some of the slides that Vanessa posted were related to some of those runs on the pre-exascale Sierra machine at Lawrence Livermore, and I presented a few slides about that during the workshop on Tuesday. Now, 2020 was a big year. That was when the system instances started being deployed. So this was release of the Flux core component with system instance support. What that means is basically the instance Flux can manage the entire cluster itself. So it's behaving a little bit more like a traditional resource manager and scheduler. In 2021, there were additional functionality and integration between Flux and the Mummy workflow, and Vanessa presented some of those slides. That was integration for RAS, or Ref Membrane Dynamics Ensemble. Then in 2023, we had Flux deployed as a system instance on some of the early access systems in anticipation of El Capitan. And then in 2024, of course, we deployed on El Capitan and then debuted at #1 on the top 500, as I said before. I should also mention, actually, stepping back, we won the 2021 R&D 100 award, concurrent with updates to the Mummy workflow. So I mentioned a couple times that Flux is a hierarchical workload manager, and it can run underneath various workload managers or cloud orchestrators. And we have deployments on a lot of different scenarios, both traditionally on HPC, but also in the cloud, on VMs, in Kubernetes, et cetera. So I'm going to get into a little bit more detail on that in a second. So I keep mentioning Flux as a framework. Well, what do I mean by that? It's actually composed of modular pieces, which is a very important piece of the architecture. So you can mix and match some of these pieces together and result in the workload manager that you need, and also integrate with external resource managers, which I'll talk about in just a second. So the components that you usually use are Flux Core, and that exposes important services for messaging, process management, et cetera. And then we have FluxSched or Fluxion, which is the directed graph-based scheduler. We have Flux Security and Accounting and PMix and many other projects as well. Now, kind of leading us toward a little bit more of the converged space, we integrate and we work quite a bit with Kubernetes, which, as I'm sure you know, is the de de facto container orchestration system for automated deployment of software and the whole life cycle of software. It's an extremely popular project. There are well over 100,000 contributors to the project, and it is kind of a dominant force in computing at this point. It is also modular. It is also composed of components. And there is kind of an analogy between these two different approaches, these two different workload managers. Both are modular, and they can be mixed and matched and combined in different ways, and we've done quite a bit of work on that. So as Vanessa talked about before, or introduced the idea of converged computing, the way that we think about this is particularly in the context of bringing together cloud orchestrators, cloud-native frameworks, and traditional HPC resource managers to create kind of a seamless, best of both worlds that enables capabilities for complex scientific workloads that are needed, such as support for MPI, but also support for services and machine learning components and training. As you probably know, cloud was designed originally for microservices or loosely coupled applications and to schedule software resources, which is kind of interesting and diverges a bit from what we traditionally do in HPC. It provides full lifecycle orchestration, including of the network for containerized applications via declarative management, which actually really helps with automation, which can also help with deployment of those sorts of cloud-native features of converged workloads. Now, on the other hand, as we all well know, HPC is excellent for tightly coupled MPI applications, those that require low latency interconnects, or low latency communications between different components of the application. HPC is also excellent and has sophisticated capabilities for scheduling and binding complex hardware, heterogeneous hardware, and of course, sophisticated scheduling and queuing, although Kubernetes is incrementally adding support for these features as well. So again, just to reiterate, I'm going to focus on kind of models for combining Kubernetes and Flux together in different, typically hierarchical formats. And this is the converged computing space that we're talking about here. So we had a project, research project that advanced convergence with Kubernetes via representative Flux-based models. So we started off with the idea of taking the scheduler, the directed graph-based scheduler, and plugging that into Kubernetes as the Kubernetes scheduler. Then we extended this quite a bit to instantiate all of Flux inside of Kubernetes and manage those pods in a hierarchical way. So in such a way, your job could run in Kubernetes in a hierarchical fashion, much in the same way that it would run on virtual machines or on bare metal on an HPC cluster. Then our third model was actually kind of flipping the script, going inside out, and instantiating Kubernetes on demand in Flux as a job. And this is the model that we're going to be focusing on today. And then the final component, which we aren't quite finished with yet, but we've been working on, is adding an elasticity to this, so you can actually grow and shrink those sub-allocations or sub-components of Kubernetes on demand. Okay, so I want to talk a little bit at a higher level about models of convergence now, like combining basically cloud frameworks with HPC frameworks, and then I'll kind of narrow down and come back to where we're going to talk about, or which one of those models we'll focus on for the rest of the talk. I want to emphasize first, though, that whenever you're combining two different systems, resource co-management requires, it first starts off with conflict over the resources, and then you need methods of deconfliction. And there are kind of classic ways to study this. Avoiding conflict introduces inefficiencies. Mediation or using meta-schedulers or brokers can be really slow, and hierarchies are complicated to implement. So the typical kind of first cut approach that a lot of folks use is to use static partitioning of a center or clusters, and this pretty clearly introduces resource fragmentation and inefficiencies. Now, there are other approaches that were delineated in a now classic paper on Google's Omega. So you have the Mesos framework, which actually used two-state or multi-level method, where you would have a top level with a holistic view of the resources, would offer those resources to lower level schedulers and resource managers. And that works really, really well when the tasks are short-lived and they're completed frequently, and also the tasks are small in comparison with the size of the cluster. Now, the Omega actually used a different kind of opportunistic approach, but the problem is, especially for gang-scheduled applications, like anything that required inter-node dependencies, such as MPI applications, this caused really expensive contention mitigation. And in the same vein, using those kind of multi-level or two-level implementations like Mesos can result in deadlocks for MPI-based applications. So our approach is much more like the hierarchical HPC and cloud or HPC approach. So we're kind of taking yet a third route here. Okay, so I'll walk through some of the things that we've tried, some of the deployment strategies that we've worked on so far. And that's first to deploy HPC and cloud alongside of it. So this should be like an easy interaction between the two different components. And the use case here is if you want to orchestrate your jobs, like your HPC jobs with AI and ML together, and also instantiate services and other cloud-native features next to each other. Examples of this are the Flux operator, which we talked about on Tuesday, and I also talked about a few slides ago, where you're deploying the entire Flux framework on a set of pods inside Kubernetes. And you also have something similar in spirit to that, which is Slinky, offered by Slurm. So the second model is deploying actually HPC in cloud within it. So in this case, the HPC infrastructure is actually isolated. Examples of this and things that we've tested are deployment strategies on EC2. You can think of, for example, VMs or parallel cluster. We've also deployed as VM sets on Azure using InfiniBand with standard instances or HPC instances, and you can also think of this as cycle cloud. We also worked to deploy on Compute Engine using Cluster Toolkit 2 with their Tier 1 networking, and we also came up with ways to kind of generalize the deployment strategies with Flux and Terraform across each one of these three hyperscalers. The next model I want to talk about is actually deploying cloud infrastructure on HPC on demand. So the cloud infrastructure may or may not be isolated, so it actually could be running on the same infrastructure that you already have. So instead of having to buy a separate cluster and have a dedicated cluster for Kubernetes, you can instantiate a Kubernetes orchestration framework, for example, on existing resources. And we had a talk about this and our initial efforts in this space at FOSDEM in 2024, and you can watch that if you're interested. Yet another approach is actually the classic bursting method. So this is bursting out from on-premises to external HPC resources. We're all probably familiar with that. The use case is if you have a portion of the job that requires resources that either aren't available or don't exist on premises. But the problem with this is that there can be difficulties in terms of security models. We're seeing a lot of interest in reverse bursting now, actually. So burst back in, so to speak. So you take a service or a portion of a workload that's actually running on cloud and then burst back into HPC. Why would you want to do that? Well, it's very, very difficult, if you haven't noticed, to get GPUs on hyperscalers currently. They're extremely expensive and extremely unavailable. However, you might have thousands or tens of thousands of GPUs on premises. And wouldn't it be great to be able to burst back in and use those resources that already exist? So we're working on prototypes and work underway with that. That's closely related to the work that Vanessa will be talking about momentarily. Okay, so we also have a hybrid implementation, which is probably similar to something that a lot of you are exploring right now, and that is where your center deploys different clusters on premises. And that has some obvious disadvantages. That means that typically you have to buy multiple dedicated clusters, which can result in fragmentation and underutilization. And it also requires a lot more investment in people, and also requires them to learn a lot more skills. So they have to do many, many challenging things to administer those different clusters. We have an example of this currently, actually two examples. The primary one is Oxeye that we're deploying right now, which can create a set of VMs and siloed network. And the idea behind this is actually to spin up services and related support components of HPC workloads. We also have a PDS cluster that is designed to spin up services on demand. So the problem with this is, what if we actually wanted our center to look a little bit more like a cloud itself? What if we wanted to be able to deploy VMs that are HPC VMs alongside VMs that are cloud native VMs, for example? Well, we're going to get back to conflict management problems. So we're going to need some form of metascheduler or broker, maybe. Or perhaps we can actually use Flux for this. So we might be able to use, or we're going to explore using Flux to schedule the deployment of VMs as well in order to deconflict these circumstances. Okay, so I've gone through a lot of different models that we've thought of and tested in terms of deploying both HPC and cloud and converged environments. And now I'm going to take it, or I will return back to Vanessa, where she's going to focus on one of these in particular. So you can go ahead and start that video up again.
Hi, folks. I'm Vanessa Sochat, joined by Daniel Milroy. We are from... Let's next talk about a new model for next generation workflows. Going back to this point that portability is now a metric of performance, and we know that traditional DAGs are not going to cut it, we have been reimagining Mumi as a state machine orchestration, meaning that it is event-driven. And so this will bring in portability, elasticity, and dynamism. And so in this new paradigm, we have goal-oriented workflows where each job acts as an independent dynamic unit. So let's walk through what that actually means. It means that we have a state machine manager that is going to be receiving and responding to events. And so because, as Dan just told you about, both Flux and Kubernetes are event-driven, what that means is that they're pluggable. You can run the same state machines using Flux or using Kubernetes. So what might you do? You'll start out by defining your state machine definition. This is a YAML file, so you define the job. So in the case of Mumi, we have the machine learning runner. That's going to generate the samples, create sim to set up the simulation, and then CG analysis to actually run the simulation. Unlike traditional tools, we actually want to define a goal. So we want to define the number of total completions that we want. We also want to define some orchestration logic, so the maximum cluster size. For example, if you're in a cluster with auto-scaling, you don't want your state machine to be like, I'd get this done a lot faster if I provisioned 10,000 nodes. And then your credit card goes crazy and it's just a bad story. So what does the state machine manager do? It basically receives this. It generates state machines where each state machine is actually a sequence of steps. So to go back to Mumi, the way it was run before was in batches. All of the ML runner, all of the create sim, all the CG analysis. With a state machine, each independent unit, each sequence of jobs can act independently. So for example, if you have one sequence where you need to repeat a step multiple times, or basically have different orchestration logic than other units, you can do that in this new paradigm. And what else can you do? Well, our state machine library also comes with metrics. So we have streaming machine learning metrics by way of River. And what this means is that you can tell the workflow, keep training this model until you reach this metric of goodness, where you don't know how many jobs that's going to be. So what you're looking at here is us doing exactly that. This is ResNet, and each of these colored boxes represents one job. So each job ran a certain number of epochs, that's on the x-axis. And so what happened at the end of each one is that we parsed the log of the job to get the accuracy, and then we checked it against the value. Is this good enough to move on to the next step? And we basically just keep going, so resulting in 5 total jobs until we reached our desired accuracy of 70%. And so what does that look like in the workflow file? Well, here's the custom resource definition for a state machine. This is in Kubernetes. And you can see under events that we have 2 metrics. We want to look at the PyTorch max accuracy. When it's greater than or equal to 0.7, that means we're going to finish the workflow. When it's under that, we're going to repeat. Very simple logic, very powerful. The state machine library has many other actions and metrics. So along with these Q metrics, this one is actually called a custom metric, meaning it's a little snippet of code that I wrote that I can use and parse the output log of this job. And so that's the really cool thing about a lot of our applications. They automatically print their figures of merit, their accuracies into the log, so they can be utilized in this approach. But we also have standard job metrics and Q metrics. So for example, the average waiting time, the average runtime of the job. If your job's taking too long, you can write a rule that says, give this job more resources if it runs longer than this. It's a very powerful setup. So what have we done with our state machine orchestration? Well, here's a glimpse at some experiments. We've run, what you're looking at here is a plot that shows running Mumi, the refactored mini Mumi, across 9 different environments. And so blue is GPU, orange is CPU, and what you're looking at are the different setups. So let me explain those first. The first is a state machine using Flux that is basically receiving the events and submitting the jobs. This is also a state machine running in Kubernetes with a state machine operator with auto scaling. This one is that same operator, but without auto scaling. This Mumi is actually a custom Kubernetes operator that we made to emulate Mumi exactly as we could with the machine learning server and RabbitMQ. We wanted to see just what Kubernetes added. And then finally, the last one is traditional Mumi, and we only have GPU for that because the cluster that we ran it on, the nodes had both GPU and CPU. So what are we actually looking at here with the white lines and actual versus theoretical best time? Well, theoretical best time, we calculated that based on taking the sum of all of the jobs. Basically, if you removed the orchestration entirely, what would the time be to complete the work, to complete the science? So any distance above that line is excess. And so what we see is that for Flux and both Flux and the state machine approaches, the 3 on the left, that amount of excess is very small. The overhead of the orchestration is small. With traditional Mumi and on-premises, it's very large. So this is one because of the event-driven design. So for example, for on-premises, when a job fails, you have to wait for some manually defined thing to check an output file on the file system, submit another job, to wait in the queue. There was also a lot of manual heuristics that were sort of hard-coded into the workload manager, and a lot of other aspects to the initial design that we refactored, such as instead of using a machine learning server, using machine learning job, what we call the ML runner, and that's what made these huge improvements. So there's a lot more in a current paper that is under review. I wanted to give you a glimpse of this work. So you're probably looking at this and you're probably like, okay, great, it's faster, but what about the cost? Well, the state machine orchestration also improves upon the total cost. And actually for this study, that wasn't the big surprise. The big surprise for us was actually that CPU turned out to be much more cost effective than GPU. And the reason for that is because we use the HPC 7G instance on AWS. That is an ARM Graviton instance. And it ran this particular component really, really well. And so that's something that we'd want to better understand. But this is actually a reason that you really, before you run a massive scale thing in the cloud, you want to understand how your workload components, each unit in the workflow, runs on the different infrastructure. So in order to support that, the state machine operator, or with Flux, I suppose, can actually be used to select instances. So this is probably a more cloud-specific case. So what you're looking at here, we actually created a workflow that used an autoscaler in the cloud to basically run the same steps, so the same exact container with the same data across many different instance types using Spot and regular instances. And so what you can see is kind of reflected in what we found, that well, Spot instances were more affordable, but they were much more hard to get. So we wound up, sticking with traditional instances. But we generally found that the Graviton instances did really well in terms of the lowest cost per simulation nanoseconds, and then just getting it done a lot faster. So now let's talk about, so that was a new model for the workflows. Now let's talk about a new model for the infrastructure. And so focusing on one of those models that Dan talked about, the idea of HPC and cloud actually working together. This shows, cloud under HPC, and we do that because we're launching user space Kubernetes under a batch job, but they're both working together. And this is a project that we call the Bare Metal Bros. This was initially presented at FOSDEM in 2024. So we started with our first prototype on-premises virtual machines at our lab. We had to do this because there's a lot of requirements that we couldn't get on our traditional on-premises clusters. This is what we call the Star Trek cluster. Honestly, I don't know why. I just thought it was a great name. And it had very simple resources. So seven nodes with Ubuntu 22.04, 8 cores, very, very small, 8 cores each, 32 MBs RAM, and not a great network, but that's all right. So we used, in user netties, you can use a rootless container technology. We wound up using Podman. We use Docker Compose to deploy it. kubeadm, there's probably many ways to pronounce that. And then for our CRI, we use containerd. OCI, we use runc. And then the CNI, the container networking interface, we use flannel. Now, what does this actually mean? It means that Flux is installed as the system scheduler. So when you shell into the lead broker, you can do Flux resource lists. You see all of your resources, but guess what? Then you deploy Kubernetes as a batch job under Flux, and you have kubectl. Kubectl get nodes. You see those same nodes, but from Kubernetes space. And one of them is the control plane, which actually still can be used as a worker node if you so choose. Now, in practice, this is why we did it at the time on these VMs. There's a lot of extra kernel modules that you need. You need C groups too, but it's all orchestrated with very simple make commands. This is Kubernetes version 2 that I worked with Akihiro to kind of put together. And in this early work, we were able to demonstrate a combined AI, ML, and simulation where we ran simulations on bare metal. They submit data when they finish to an API server that was running in user space Kubernetes. And then we were able to go on the other side and run more simulations and then ask the machine learning server to use one of 3 models, or actually all 3 models, to make a prediction for what the runtime would be based on the parameters. Very simple, but very, very cool to see these 2 things working together. So at that point, though, we also ran lamps and we saw quite a bit of overhead. So on the left box in the red, that's Kubernetes running in the background. We did that because we wanted to see if just like having Kubernetes running would add overhead. Next to it is just on the virtual machine. So we see very little difference between a bare metal, and actually that's the virtual machine run, and a container run, which is Singularity. The problem is that there's huge overhead. It's like, takes twice as long basically with Kubernetes, but we expected this. So Kubernetes uses slurp for net NS, which requires additional processing of packets with a tap device. And given MPI, we expected this slowdown. It's well documented in the literature. So we also wanted to look at overhead with machine learning. So we ran MNIST. So on the left side of this figure, the figure is showing basically the discrepancy between running on the virtual machine, that's in red, and then Kubernetes. Again, takes about twice as long when you're running in Kubernetes, not great. The plot on the right is basically running on just one node in the same environments. And we did that just to make sure. It's kind of a sanity check. Like, we believe this is the networking. If we remove the networking from the equation, do we still see that slowdown? We absolutely do. So it's a networking, right? Yeah, it's the network. Can we test that? Let's do experiments too, and let's bypass that network. Let's go to Amazon and let's use the elastic fabric adapter. And so this is a design of the elastic fabric adapter. It's basically using libfabric to bypass that networking, traditional Ethernet space. Will it remove the overhead? Most of it. So this definitely looks better. You're looking at, again, lamps for up to 32 nodes. And what we do notice is that there's still a little bit of overhead. And so we're still working on investigating that. But using this bypass approach is, we believe, the way to go. So what about a different bypass? What if we use InfiniBand to the Batmobile? And he put on his super sunglasses and then not the Batmobile, just the cloud console, because, zero cloud console. And then the robot on the left is like, where did you get those glasses? And the robot on the right is like, put them back in mom's car when you're done. These are robot bros, remember? So, So we ran InfiniBand, again, lamps on Azure, Microsoft. This result looks very similar, maybe slightly less discrepancy between the two, but again, there's still some overhead that we need to investigate. Time for on-premises? Yep. And just to be clear, put those sunglasses back. I'm just kidding. So in summary, we have demonstrated this approach that brings together the best of both worlds between cloud and HPC, the bare metal bros running them together, and also imagining new paradigms for running workflows that are event-driven. We think this is a really awesome, positive future to move toward for cloud and HPC. So on that note, thank you so much for having us today. This is how you can reach us if you need to, and we will open it up for questions.
Awesome. Thank you so much. Questions? Long day. Oh, we have Vanessa here. Thank you, Vanessa. Oh, we cannot hear you.
It's like yesterday.
Now it works.
There we go. Hi, folks. Good morning. I mean, not good morning.
What time is for you now?
I got up at 4:30 a.m.
Oh, that's. Thank you so much. I guess. Okay, questions?
So thank you very much for the presentation. Flux looks very cool. I do have a question regarding your burst out, burst in. How do you manage data movement? Right, because that is usually the main challenge when we talk about bursting in or out of the cloud is for large data sets. Is Flux taking care of moving the data, or can we tell Flux to take care of it, or do we have to take care of it on our own?
Do you want to use this?
Yeah, to be clear, a lot of these models are in current development and are experimental. So we don't know the answer to that yet. That's an excellent question. Basically, what we've done is we've demonstrated proofs of concept for a lot of these. They're not being used in production yet. So very good question. I don't know who is going to perform the data movement. There are sub-projects of Flux that could potentially do that. There's something called Flux Dyad, but we haven't tested that before. So.
To add to that with bursting, you typically wouldn't want to, for example, run an HPC workload that spans between like AWS and on-premises. The idea is that you'd have a scoped piece of work, perhaps using GPUs on-premises that you would send back to on-premises.
This is usually the weakest, the most fragile component. Not just I believe that there is no workload manager that has an answer for this so far. More questions? So I have to say that over the last 2 days, we had a lot of conversations with the audience about Flux. So you have really made an impact. And the song, well, the performance that you did the day on the workshop, it was awesome.
Thank you. And if anyone wants to continue discussing Flux, obviously Dan is there, Hobbs is there. Hobbs, raise your hand and wave. We have a Slack, we have a list. Please reach out to us to talk with ideas. We love to collaborate, we love to talk, and thank you so much for having us today.
Thank you. So I do have one more question for Flux adoption in industry. One of the barriers that we see is integration with vendor-provided software, like Schrödinger, for instance, or any others. Are you working or are you in contact with some of these vendors to have them integrate their software? Do you expect this to happen naturally as El Capitan now is running Flux?
I expect we're going to have more integrations, yes. I think, as you rightly suggested, one of the focuses has been in the last several years making sure that Flux works correctly at scale on El Capitan. And now that that has happened, we can kind of focus on all sorts of different integrations that we've been planning. So that's, I think, the best answer I can give so far.
One more question.
Hello, thanks for the nice talk. Do you envision Flux replacing Slurm in the short term?
I think given the share of clusters that are running Slurm, that is unrealistic, but I think we'll see naturally as people notice that the Flux features are really useful, that we anticipate our share of the clusters to increase.
Okay, so thank you so much. So there is more.
Thank you. Thank you very much for having me. Been really excited to present here. It's a great audience and a great venue too. So.